Okay, last time we were talking chapter 10. We almost finished it, so we can wrap up that little part of it. So last time we got into kind of specific heat, and there's an equation that goes with specific heat. It's Q is equal to ms delta T. Q here is heat or energy. It has units of typically joules or calories. That is the mass, which is usually grams. S is the specific heat capacity. Which is joules per gram per degree Celsius, or calories per gram per degree Celsius. And change in temperature is in degrees Celsius, and that is our final temperature minus our initial temperature here. We could use this obviously to figure out how much heat or energy is being given off. We can also figure out all kinds of things, the temperature and so forth. Remember that if you calculate Q and it ends up being a negative sort of value, that is going to be an exothermic process. Heat and energy is going to be released. If you calculate it and it's a positive value, then it's going to be an endothermic process. As we talked about, specific heat capacity is basically the amount of energy that's required to change 1 gram of a substance by 1 degree Celsius. And you do need to know the specific heat of liquid water, which is that 4.184 number joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. We typically around here usually roll with the joules one of it, but that is also 1 calorie per gram per degree Celsius. That's also the conversion, right? 1 calorie is 4.184 joules. That's the conversion to go between calories and joules. Now, we also talked about the idea here that very often we'll use something like water and we'll put something into water, and we can find what's happening in terms of water, in terms of the energy it's either absorbing or releasing, and that will allow us to figure out, sort of what's going on with whatever we put into the water. So we talked about sort of, we took it like a hot piece of metal and we tossed it in. Because that metal is hot, again, it's going to transfer the energy from the metal to the water, as heat will transfer from hot to cold. And we can basically figure out what's going on with water because we do know the specific heat capacity of water. So really all it requires us in most cases is to get the mass of the water that we're measuring, and also use a thermometer basically to get the temperature, very similar to what you're going to do in lab today. Any questions on that there? We also talked about in that relationship, the relationship, for example, of like Q of the metal or some type of object you put in there is equal to Q minus Q of the water. Again, the idea here is whatever energy that, say, the water picks up, all of that should have came from like the metal or something objects that you put in there, or vice versa. Whatever energy the water should lose would be the same amount of energy that would be picked up by the object that you put into the water. So again, just by simply following the change that's happening there with water, we could really determine sort of what's happening in terms of energy. Any questions on that there? All right. So one of the ways you can do it, very much like what you're going to do today, is do constant pressure calorimetry. And it can be just done with 2 styrofoam cups, like we're doing today. And that's a pretty well insulated sort of system. You put some water in there, put a lid on it, and put a thermometer in there. And again, you could do your reaction in that styrofoam cup. And like I said, you basically can just simply use the specific heat equation and figure out how much heat or energy is being absorbed or released in that reaction. And you can figure out sort of what's going on. When you do this type of calorimetry at constant pressure, which it typically is in the laboratory, uh, when you calculate Q, it is equal to the delta H in this case, or the change in enthalpy that's occurring. Thank you. And so it's a very simple way with just some coffee cups and a thermometer. You can very simply figure out the delta H of a particular reaction. We could also do this, as I mentioned last time, for example, with not a solid dumping in there, but actually taking two chemical reagents that are aqueous, and you can put them together and do this sort of reaction and measure the change in temperature. And again, because aqueous, which usually has this aqueous symbol next to it, is basically water-based in a lot of cases. even though we may not know the specific heat capacity of the specific chemicals we're using, we could pretty well estimate it because it's mainly water. So you still the specific heat capacity of water, and you can just put the two reagents in there, follow the change in temperature, and do this calculation. And very simply, you could figure out the delta H for a particular reaction or a change in enthalpy for a particular reaction. All right. We also talked about nutritional calories last time. And again, a reminder that each of those sort of nutritional calories have a certain caloric value, which is basically what this is. And carbohydrates and protein are 4 kilocalories per gram, and fat is 9 kilocalories per gram. So in this particular problem, we had some cereal that had 22 grams of carbs, 7 grams of fat, and 10 grams of protein. So as we talked about last time, you basically take the grams of each of those sort of components and multiply it by the caloric value. And it'll basically give you how many calories you're getting from each of those things, carbohydrates, fats, and proteins, because remember, one nutritional calorie, which is a capital C, is equal to 1,000 of the little calories, little c, which is 1 kilocalorie. So kilocalorie is basically a nutritional calorie. And in this case, you would have 191 calories per serving. And since you got ate 2 servings in this case, it would have had about 382 calories. So that's another sort of unit of energy, more so for nutrition sort of calories. We don't come across it too much, but in case you do, there is a difference, as we talked about, again, between the capital C and the lowercase c there. Now, let's talk a little bit about thermodynamic sort of equations and thermochemical equations. And sometimes you are in a situation where you may have the delta H value given to you for a particular reaction. And maybe you don't need the reaction the way it's written, but maybe you actually need the reverse of that reaction. So for example, here, this is ice going to liquid water, has a delta H value of 6.01 kilojoules per mole. But if we want to know, for example, what the delta H would be if we went the other direction, if we started with liquid water and we ended with ice, we basically would reverse the reaction. So as we talked about in this chapter, to calculate the delta H of a reaction, it is the delta H of our products minus the delta H of our reactants. So when we reverse the reaction, what happens is our products become our reactants and our reactants become our products. So the difference is still going to be the same number, but the sign will change. So as you reverse a reaction, you change the sign of delta H. So if it was positive like it was in this case, it would become negative. And obviously if it was negative to start with and we reversed it, it would become positive. Now, there are some other things that sometimes occur. Maybe you're looking at a reaction where you are going from solid to liquid, but you're actually doing 2 moles of water instead of 1. And that's what the number in front represents, is the moles. And in this case, what you would have to do in this reaction is, if you only had this guy, you essentially would have to multiply the entire reaction by 2. And that's how we get, obviously, the coefficients there. And how that affects the delta H in a reaction is you actually would multiply the delta H value by 2. And we would have 12 kilojoules for our delta H versus, obviously, 6 for one of them. The same is true, though, in some cases you may perhaps be starting with this reaction. And again, maybe you're not interested in how much energy for 2 moles of water, but you're actually interested in how much for 1 mole of water. So if we were starting with this one and we wanted to end with the top one, which is H2O, goes to just H2O. What we would do is we would take our delta H, obviously from above there. We would obviously go through and we have to divide everybody by 2. We would then also divide the delta H by 2 as well, and that would give us back to our 6 kilojoules per mole. So sometimes you do have to manipulate these sort of equations, and depending on what you do, these equations, it will affect the delta H value that is sort of given for it. Because when you see a delta H value is specific for how the equation is written, so if you kind of do something to it, it will affect it. Now, where this really comes into play is something known as Hess's law. And Hess's law is an idea that not all reactions basically occur in like a one-step process. Like, for example, if you had a reaction, you look at like A plus B goes to E plus F, you may be tempted to think that that's all just going to occur in like one move and one step. And in fact, a lot of reactions actually occur as many individual reactions that when you add them together, you get the overall reaction. So for example, this overall reaction here might actually occur from like first happens A plus B makes C plus D, then that has a certain delta H value. And then C plus D makes E plus F, that has a certain delta H value. And if you add both of those reactions together or equations together, you could always add equations together. And when you do add equations together, whatever's on the left-hand side of the arrow in one equation and on the right-hand side of the arrow in the other, that's the same. Could either completely cancel out or just reduce down. So if we look here, we have C on the left and we have C on the right. So they're essentially going to cancel each other out. You could think of the arrow like an equal sign, like you're going to subtract it to the other side and it's going to basically cancel each other out. Same thing here, the D on the left would actually cancel out the D on the right. And what we're left with at this point, since we have nothing else that will sort of cancel or reduce down, is everybody on the left stays on the left of the arrow and everybody on the right stays on the right. And that gives us our overall reaction that we're looking for. Now, if we wanted the delta H for this reaction, we would get it by taking the delta H for our final reaction there would be the delta H of the first reaction plus the delta H of the second reaction. And we would add them together and that would give us our overall reaction. So this is what Hess's law is. We used to teach in this class, but not anymore. So you'll see it when you go to 1A, but it's basically an idea. You can just take a bunch of individual reactions, and sometimes what you have to do with those individual reactions is sometimes you have to kind of reverse them, sometimes you have to multiply them by a number, sometimes you have to divide them by a number so that you can get everybody in the right spot so that when you add them together, you get that overall reaction. Any questions on that? So for us, you just simply need to know what happens when you sort of manipulate an equation. So again, if you reverse a reaction, the delta H changes sign. If you multiply by a common number, multiply by 2 against the reaction, or 3 or 4, you would multiply the delta H value by the same number. And if you divide by a common number, 2, 3, 4, 5, whatever it may be, you would take the delta H and divide by that number. Any questions on that there? That is that chapter. There it is. All right. That is the last part of what is going to be on next week's exam. Yeah. So we're going to go off to the next chapter as soon as I find it. Let me see here. We are off to chapter 4. So we're going to go backwards, I hope. That was the right chapter. So in this chapter, we're going to talk about the atom. We're going to talk about protons, electrons, neutrons, periodic table, and a bunch of stuff, I think. So we're going to talk about some experiments that led us to an understanding of the atom. But first, we're going to talk a little bit about formulas of compounds. And a compound, as we talked about, always contains the same relative number of atoms and elements. Remember that to be a compound, you do need atoms of different elements. So remember that is how it differs from just a molecule, which is a more general definition of all you need is 2 atoms present. But for it to be a compound, you do need, again, atoms of 2 different elements at least being present. So water, for example, always will contain 2 hydrogen atoms for every 1 oxygen atom. And we do express a chemical formula that shows us the different types of atoms that are present in a compound. And we do use the symbol to indicate that. And we also use a subscript. So when we look at something like water, again, the subscript always goes to the element to the left. So that would mean we have 2 atoms of hydrogen. Most of the time in chemistry, we really don't write 1. So if there is nothing written there, it is assumed to be 1 of something. So there technically would be 1 atom of oxygen. Uh, so when we do write these chemical formulas, again, we use our symbols and those subscripts. Uh, and when only one is written, or when only one atom is present, again, we don't write anything. So always to the left is what it is. So again, if we have something like N2O5, this would have 2 atoms of nitrogen and 5 atoms there of oxygen. And same thing here, nothing written next to the carbon. So 1 carbon, 2 oxygens, 1 nitrogen, and 3 hydrogens in this case, again to the left there. All right, so why don't you take a second here and write the formulas for each of these descriptions. Okay, let's take a look. So first one is a molecule that contains 6 carbon atoms. So carbon is C, and again, we would use a subscript of 6, and 6 hydrogen atoms. So H and 6, again, our subscripts go to our guide to our left. A compound that contains half as many calcium atoms as chlorine. So calcium is Ca, chlorine is Cl. And we got a compound that contains half as many calcium as chlorine. So for example, if I go with 2 chlorine, half of 2 would be 1. And that would give me my calcium obviously as 1 and my chlorine as 2 in this case. And lastly here we have a compound that has equal numbers of sodium and nitrogen. So sodium is Na, nitrogen is N, equal numbers there. And 3 times as many oxygen atoms. So each of these are 1, so 3 times would be 3 oxygens. So we would end up with something like that, NaNO3, which is sodium nitrate. Calcium chloride on the middle there, and a little benzene on the top there. Any questions on any of those there? Okay. And again, those tell you how many atoms of each of those. Later on, we will learn in chapter 8. It'll also tell you how many moles of each of those elements are also present as well. All right, so we're going to now talk about the atom and sort of some important experiments that led us to the understanding of the atom and sort of, where things are and how it looks. As we go through it, we'll talk about kind of what you need to know from those things. So early atomic theory started way back when with philosophers believing that all matter was composed of these really small, indivisible particles, which they called atomoses, which means uncuttable or indivisible, kind of indestructible was sort of the thought of what atoms are. So it's kind of early on. A lot of things were sort of thought of, and they believe that most natural materials were mixtures of pure substances. And a pure substance could be either an element or a compound. And the law of composition means that a given compound always has the same composition regardless of where it comes from. So, for example, as we talked about, water has H2O, and pretty much the mass of hydrogen is about 1 gram, if you will, rounded a little bit. Oxygen is about 16 grams. So when we think of the mass of water, that's always basically about 2 grams of hydrogen for every 16 grams of oxygen. We divide them both by 2, gives us for every 1 gram of hydrogen, there's always 8 grams of oxygen. So no matter where you find your water, however it's bottled, the water part of it will always have really that composition in terms of mass, for example, here of how many grams of hydrogen there is to grams of oxygen. Now, one of the earliest sort of ideas about atomic theory was one done by Dalton. And Dalton's atomic theory was done by a guy named John Dalton. He kept records of weather every day of his life. He never married, but he did like to go bowling on Thursdays, which clearly, if you learn nothing else in this class, that is the day he liked to go bowling, right? That's going to definitely be on the exam, so make sure you don't miss it. So it's not Friday or weekend or half price Thursday. So maybe other Thursdays half price would be good. But One of the things he's really known for is he formulated sort of a precise definition of what we call atoms. And it is a theory, so as we'll talk about, there are certain parts of Dalton's atomic theory that are not really considered correct anymore. And again, that's what a theory is, something that maybe is not always correct, can be revised, maybe found parts are right and parts are wrong. So some of the important parts of Dalton's atomic theory are what are up here. And basically, he said elements are composed of these extremely small particles called atoms, these kind of indestructible sort of particles like they thought of before. And that is, again, one of the things that is not so correct anymore. Atoms are not necessarily indestructible. You can, for example, in nuclear reactions, change one atom to another by, kind of playing with what's in the nucleus. So that's one of the parts of his atomic theory that's not so correct anymore. He said that all atoms of a given element are identical to each other. They have the same size, the same mass, and chemical properties. This is another one that is not really correct anymore. The existence of isotopes, which we'll talk about in this chapter. Isotopes are the same element, but they do have different masses, which means obviously if they have different masses, they're not identical to each other, right? So that is one thing that's also not correct anymore in terms of his atomic theory. Atoms of one element are different than atoms of another. That is good. Again, if you have an iron atom, it will have different sort of properties or characteristics of, say, a copper atom. They will be different, for example, in the number of protons they may have and so forth. A chemical reaction involves only the separation, combination, and sort of rearrangement of atoms. That is correct. Again, that is basically what happens in a chemical reaction. In a chemical reaction, all we are doing is breaking electrons, which are bonds, and we're just rearranging the elements. So we never like lose an element along the way. We never make a new element along the way in a chemical reaction. We just kind of break all the pieces apart and reassemble them as new compounds and substances on the product side of the reaction. The law of conservation of mass says that matter can be neither created nor destroyed. So because we have sort of in reactions that conservation of elements, which means if we started with like 6 carbons on the left-hand side of the arrow, we will end with 6 carbons on the right-hand side of the arrow. Again, they may be in different places on each side, but each carbon itself has 12 grams about of mass. And that means you will have the same mass of carbon on the left-hand side of the arrow if you add up all the carbons as you do on the right-hand side of the arrow, again, because you don't lose any elements along the way. So these are the main parts of Dalton's atomic theory. Once again, atoms being indestructible and atoms of the same element being identical. Those are, again, two parts of Dalton's atomic theory that were later found not to be correct. All the rest is good to go. Now, what did Dalton picture atoms as? He pictured them as compounds or a collection of molecules. And you can think of, obviously, like our elements, which are on the periodic table, as kind of like the alphabet. And again, different combinations of um, of letters will give you different words, and same thing, different combinations of elements will give you different compounds. Even if you're using the same two elements like we are in this picture, everybody has basically nitrogen and oxygen in there. Depending on how many of those you have, how they are bonded together will give you different compounds, and they will have different properties because of what is bound together. But they will always come together in a certain ratio. That is always a whole number ratio in terms of their mass as to how they come together. So, for example, if we look at nitrogen and NO here, nitrogen is about 14 grams and oxygen is about 16 grams. So, if you take 16 divided by 14, you got like 16 grams divided by 14 grams. You got about 1.14-ish in terms of the ratio. Now, in this case, if we do kind of the same thing there for this guy, we basically got, again, nitrogen at 14 grams. We got two oxygens at 16 each is 32 grams. 32 grams divided by 14 grams gives us a ratio of like 2.28. That is about, we have twice the amount of oxygen as we go this way, and we got twice the ratio of mass in there. So they always kind of come together in that kind of whole number ratio as they put together. When atoms come together to form compounds, they're always whole numbers. You never get like a half atom kind of coming together or anything like that. It's got to be whole numbers when they come together. So we end up with kind of that ratio by mass because they do come as whole number sort of entities. We'll always kind of have that same whole number ratio when we maybe add more to it. Now, let's talk a little bit about the structure of the atom. Based on Dalton's atomic theory, there was a lot of things that were thought of, but it's really defined as the basic sort of unit that could come into chemical combination. The atom is the basic representation of all the elements that we have on the periodic table. So a lot of investigations from 1850 to about the 20th century understood that the atom was a really small sort of particle. But it actually was made up of even smaller particles, which are known as subatomic particles. And those you may be familiar with, those are our protons, as we'll talk about, which are positively charged. Those are our electrons, which are negatively charged. And they also have neutrons, which have no charge. So there was this understanding at the time that the atom is very, very small, but even though it's really, really small, there's still even smaller parts that make it up. And we're going to talk about really some experiments that led us to the understanding about electrons, some of its properties, protons, where they're sort of at in the atom, and also neutrons, sort of where they sort of end up as well. So we're going to start with the electron, and one of the biggest sort of advances, if you will, in the idea of the electron and what's going on in the atom was really a big concept in chemistry, which is opposites attract each other. Yeah. So much like in life, opposites attract each other. So, if you have two positive things, they do not like to be near each other. They were repelled from a number, right? We got two positive people. They can't stand to be near each other. That's too much positivity. You got two negative people or two negative charges. They also want to repel each other. Much like in life, they say you should find somebody that's maybe a little opposite of you, right? So a positive and a negative attraction are always attracted to each other. So that is a really big sort of idea here in chemistry. The idea of positive negative attraction is actually the basis of the ionic bonding that we'll talk about. That is what holds, for example, something like sodium chloride together. There's absolutely no sharing of electrons. It is simply the attraction between the sodium ion that has a positive charge and the chloride ion that has a negative charge that kind of sticks each other together. It's that opposite charge attraction. So when they were doing a lot of these experiments, it was really beneficial, this idea of opposites attraction. This is what is sometimes referred to as electrostatic attraction. And they used in a lot of experiments, as we'll talk about, a lot of radioactive particles. And three kind of big radioactive particles that were used in some of these experiments. There are alpha particles. And alpha particles are radioactive particles that essentially have a positive charge. There are beta particles, which are also radioactive particles that have a negative charge. And there's gamma rays. And gamma rays are just pure radiation. They have like no charge associated with them. So a lot of experiments involve the use of these radioactive sort of particles to investigate the atom. And that in combination with some other things that were used, things like an electrical field, right? And if you have an electrical field, what you essentially have is like a positive side to that field and a negative side to that field, right? And they could kind of determine, for example, the charge of something by how it is affected by an electrical field. For example, if I shot a particle through here and I wasn't sure what type of charge it had, and it bent towards the positive side of the electrical field, I should probably make a good guess that that particle has what type of charge. Should have the opposite charge, right? Because it's going to be attracted to it, so it should have a negative charge. If I shot something and it kind of bent towards the negative side, I would probably know that that guy has a positive charge, right? And if I shot something and it pretty much was undetermined there or unaffected by the electrical field, it most likely had no charge because it was able to sail right through. So a lot of experiments sometimes use electrical fields. Sometimes they use magnetic fields, which works the same way. There's like a North Pole, South Pole, kind of same idea. And using the advantage of these things that has charges to help them investigate. Any questions on that there? All right. So one of the earliest sort of investigations came about with the CRT, and the CRT is a cathode ray tube. And you may be familiar with cathode ray tubes. They used to be in old TVs, like the ones you put on the floor. In the back, they have like a picture tube. Old computer monitors that have like the big back to it and stuff like that. If you see one in a picture, that is what those are, CRT monitors. So what it is basically, it has basically a charged side, a negative side, and a positive side. And it shoots a stream of negatively charged electrons, basically, or negative charged particles. And because of the opposite attract, it's going to go away from the negative side and head towards the positive side in this sort of field. And a lot of times what they'll do is put something on the screen here, and you can actually see a fluorescent material. You can kind of see where it's hitting the screen. So this was a really big advance in sort of the understanding of the electron. So the cathode ray tube was used a lot in investigating the electron. And as I mentioned, it's basically this negative surface stream of particles that heads towards the positive side. And again, you could kind of do that. And as we talked about there, again, with these different charged particles, electrical field, and also a magnetic field, north and south sort of magnet there. And this is a cathode ray tube. I think it'll play, maybe. Maybe. Let's see. Or not, maybe this one will play. Let's see.
This is a cathode ray or Crookes tube. It produces a beam of electrons, as do television sets and computer monitors. A luminescent material has been painted on part of the inner surface of the tube. It produces light when electrons strike it. The electrons originate at the cathode of the tube. The long, thin object entering the scene is a bar magnet. The position of the bright spot on the screen can be changed by moving the magnet near the beam of electrons. This process is analogous to adjusting a television picture.
So you can see the little beam there. That's their kind of negatively charged particles affected obviously by a magnet there. And that's why it's affected again by a magnetic field and an electrical field. And that's what you used to do when your TV was bad. You called the TV repairman to come out to fix it. You didn't just go to Costco and grab a new one there, throw it on the back of the truck. And the back ones, again, if you ever had an old TV, or maybe some of your family has an old TV, you take it open, they actually have a picture tube, which is basically a cathode ray tube in there. Like I said, old computer monitors, nothing like this, that have the big back with those. So the CRT was used by a guy named Thomson, and J.J. Thomson did a lot of experiments with this cathode ray tube, as you can see right there. And basically, one of the important things that came out of Thomson's experiments with the CRT tube was that he was able to figure out the charge to mass of an electron. So by doing experiments with the cathode ray tube, he was able to figure out that the charge to mass of an electron was minus 1.76 times 10 to the 8. C is a coulomb. A coulomb is a unit of electrical charge, and grams is a mass unit. So coulombs per gram, again, charge per mass of an electron. And this was a good sort of first understanding of some of the properties of electrons. Clearly, they're negatively charged, as you can see by the difference in the field there, positive side, negative side, electrons going towards the positive side. And the next really important sort of experiment that goes with Thomson was one that was actually done by a guy named Milliken. And Milliken did what is commonly referred to as the oil drop experiment. And essentially, the oil drop experiment was he used a electrical field here in this chamber, and he shot in droplets of oil. And what would happen was it had this little opening here, and the drop of oil would start to fall by gravity. And as it would fall by gravity, it would basically pick up a charge. And what he was able to do was essentially adjust the electrical field in such a way that basically the droplet just kind of hung there. It didn't fall, it didn't go up, down, just kind of was suspended there. And what he was able to do is really sort of dial in, and calculate the actual charge on an electron. So Milliken did this experiment. I think this might work here, maybe. It is. So that was sort of his experiment. He shot the oil droplets in, went through the little hole, adjusted the electrical field, and basically that oil droplet was just sort of suspended there. And again, by doing some calculation, he was able to figure out the charge of an electron was minus 1.60 times 10 to the minus 19. So these two experiments are really important because we had Thomson that figured out the charge to mass of an electron. We had Milliken that figured out the charge of an electron. And if you do a little stoichiometry sort of calculation here, if you take the charge and you divide it by the charge to mass of an electron, charges cancel. The mass of an electron could be determined through these two experiments or the results of these two experiments. And if you do that calculation with their numbers, you end up with the mass of an electron here. And that is the mass of an electron. And it is 9.09, 9.11, depending on your book, times 10 to the minus 28. And that is grams. You will sometimes also see it in kilograms, and it's basically the same number to the minus 31 kilograms. So sometimes you'll see it in kilograms or grams. And that is the mass of electrons. So the first two things you need to know, obviously, is the cathode ray tube. Obviously, Dalton's atomic theory. But besides Dalton's atomic theory, the cathode ray tube, sort of what it is, and Thomson using it, figured out the charge to mass of an electron, followed up by Milliken's oil drop experiment, a little bit about what it was or what it did, and the charge of an electron. And again, using both of those gives our mass of our electron. By the way, that is a large number, small number. That is a super small number, right? It's like 28 places to the left and put a bunch of zeros, right? So it's going to make it really, really small. Now, the rest of the atom was also sort of investigated, protons and nucleus, and the nucleus. We're going to talk about how we kind of got there. So by the early 1900s, there was a couple of things about the atom that was sort of thought to be true. And one thing was that obviously they contained these negatively charged electrons, and they also felt that the atom was neutral. And what that would mean is if we already have negatively charged electrons and the atom is neutral, it would also have to contain something that is positively charged to balance out all electrons. And around the turn of the last century, the accepted model of the atom was one that was proposed by Thomson and is commonly referred to as the plum pudding model of the atom. And basically, the plum pudding model of the atom is a sphere of positive charge. So basically, the positive charge is spread out all over the atom. The sphere of positive charge is spread out. And embedded inside the atom are these negatively charged electrons. So you got these negatively charged electrons embedded inside the atom. And it was believed at this time that most of the mass of the atom was the electrons. But at this time, this was sort of the version of the atom that they believed. We got this positive charge spread out, and that's why they called it the plum pudding model. The positive charge is like the pudding, kind of spread out on your dish. and the electrons embedded in there like raisins, it's tossed in the kind of pudding and stuff like that. So you got this kind of smear of positive charge, negatively charged electrons embedded inside, and most of the mass of the atom is the electrons. And this was sort of the believed version of the atom, again, looking something like this, with our positive charge spread out there all over. Now, this was really sort of the accepted model of the atom until really the next big sort of experiment came along. And this was done by a guy named Rutherford. And Rutherford did the gold foil experiment. And much like it sounds like, what he did is he took alpha particles. So remember, these alpha particles are the positively charged radioactive particles. They're really just helium, but they're positively charged radioactive particles. And he shot at pieces of gold foil and other metals. And what he expected to happen was one thing, and what actually happened was something else. So, for example, what he expected to happen, if we go back to sort of this model of the atom, this is all positive charge, the blue part of it in there. And what he expected to happen was he was going to shoot these alpha particles, which again are positively charged particles. They're pretty heavy. They're moving really fast. He expected when he shot these alpha particles for them to go through, and there would be like a little bit of sort of deflection because they're going through this kind of jelly, if you will, or putting a positive charge. So they're going to hit it. So kind of like if you took a piece of paper and it was all this was the positive charge, right? And you held it really tight on one end, somebody held it really tight on the other end, and we shot a pen or something at it really quickly, right? It'd probably be able to pop through there, right? But it would kind of deflect a little bit as it tried to pop through the paper and it came out the other side. And then we expect this sort of deflection because, again, ultimately you're shooting positive at positive. It will be able to pop through there because it's moving quick, but there would be some deflection. And he was really surprised when he did this experiment was that's actually not what he saw. What he saw was when he shot those alpha particles, pretty much they went straight through with like no problem, right? They were undeflected. So they did not have any problem going through. And he did notice that every so often there would be an alpha particle that actually was deflected at a pretty big angle and would even, for example, come back at the source. So if we think about sort of what that means, if we shot these alpha particles and it went through with no problem, didn't deflect or anything, what did it hit? It pretty much hit nothing, right? So like if I took my pen and I tossed it that way with nothing in the way, it's going to have no problem, right? It's just going to go right through because there's nothing in its way, right? But he did still see that every so often these alpha particles would bounce off at these really, really large angles, right? And that would mean that it had to hit something that was very, what type of charge? It had to be very positively charged, right? Because the only way to get those alpha particles which are heavy and moving really quickly to bounce off at really large angles is it had to hit something very, very densely positive to make it ricochet off at those large angles. And what he basically had to say as a result of this was when we look at the atom, I don't think this is correct. This cannot be the correct model because if we have the positive charge basically spread out all over, my alpha particles should be able to pop through anywhere with a little bit of deflection, no problem. But what he discovered based on these every so often these particles bouncing off at large angles was the positive charge could not be spread out all over. It had to be really, really concentrated in one spot, right? So for example, if I took my paper instead of the positive charge being spread out all over, and I folded my paper with all the positive charge right down into a super small amount, right? Really densely populated positive charge. And I throw my pen at it. I'll try one I won't break, right? It is going to bounce off at a pretty large angle because now it's pretty densely positively charged and it's going to repel it really much. So he had to kind of move away from the plum pudding model to this idea, as we'll talk about, that really most of the atom is empty space, which is why those particles had no problem kind of going through and they were undeflected. It contains this really dense positive core that is positively charged, and that is what we call now the nucleus that's positively charged, and that accounts for those guys that hit and bounce off at really, really large angles. So let's take a look at this one here, maybe.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electron. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle. In 1910, Rutherford...
So you can see on the screen that most of them are hitting straight across there, not going anywhere, but every so often it lights up.
The alpha.
So as we saw in that animation, most of them no problem going straight through, but again, every so often it would sort of hit at these large angles. So as I mentioned, we had to kind of move away from the plum pudding model of the atom to a new model of the atom, sort of proposed based off of Rutherford's sort of findings, which again were, most of them were undeflected. We had these guys every so often, kind of bouncing at these large angles, kind of like shooting a gun at a piece of paper and having the bullet bounce back at you. Not so great. So on the left here is where they expected to happen going through. And again, what we see on the right there is really what did happen. And again, that makes us have to move away from that plum pudding model to sort of the actual version of what the atom is. Again, based on Rutherford, the atom is mostly empty space. Again, that is what accounts for those particles not having any issues going through. It does contain a very dense positive core, which is our nucleus. And later found that inside the nucleus, that is where we find our protons, which are positively charged, which would account for why it's so densely positive. And later on, like in 1930s, neutrons were discovered to also be part of the nucleus. And another really major difference between sort of the plum pudding model and sort of the modern model here of our atom is most of the mass of the atom is actually the nucleus. So the nucleus is what comprises of most of the mass of the atom. So we have basically this nucleus that has positively charged protons, no charged neutrons in it from the 30s. And all in that empty space is what is sometimes referred to as the electron cloud. That is where electrons are. And as we'll talk about, they do not travel in pretty circles. They are traveling randomly about the nucleus. Is there any type of attraction between the electrons and the nucleus? The answer is yeah, it's the same positive negative attraction that we've been talking about. Electrons are negatively charged, the nucleus is positively charged overall because of the protons. So there is an attraction between those things, and that's why, for example, electrons just don't fly away, right? They're attracted to the nucleus, they're kind of held within the atom. And also, as we'll talk about in later chapters, that's why there are certain electrons that are actually farther away from the nucleus. They're actually involved in bonding. They're known as valence electrons. Because they're further away from the positively charged nucleus, they're not held as tightly as electrons closer to the nucleus, which are referred to as core electrons. They're held a lot tighter because they're closer to that positive charge. One of the things about the opposite attraction of the charges, positive and negative, is the strength of that sort of attraction increases with the size of the charge. So if you have something, for example, that's +3 and -3, it's going to be held together a lot tighter than if you had something that was +1 and -1 when they come together. So as the charges increase, the positive and negative charges, the attractive force between the different charged particles becomes stronger and they're held tighter. And that's what we also see with electrons as well. Any questions on that there? So obviously Rutherford, you know his experiment, kind of what he did. He shot alpha particles You also need to know kind of what he expected to happen, right? And what actually did happen. And you need to know, obviously, what the plum pudding model was going into it, and obviously the version of the atom, which we currently still use, coming out of it. Any questions on that there? So here's just a table of some of the experiments we've talked to up to this point that kind of led us to the understanding of the atom, and again, sort of the major sort of findings that came out of that. Continuing on with sort of our investigation of protons, as we talked about, they are found in the nucleus, and they are positively charged. And protons have a mass of 1.67252 times 10 to the minus 24. And if you remember, our electrons had a mass of 9.09 times 10 to the minus 28 grams. Yeah. When you compare the masses of a proton to an electron, a proton is a lot heavier than an electron. By the way, when you compare negative exponents, the smaller negative exponent is the larger number, by the way. And it's about 1,840 times heavier than an electron. And that also sort of helps us think about Rutherford's idea that the nucleus is most of the mass of the atom. Because in the nucleus we have protons, and each proton is about 1,800 times heavier than any electron flying around. So that does make sense that the nucleus is most of the mass of the atom, because that's where we find those protons. Also why when they are in there, they're much heavier than any electron or any particle kind of flying in, like the alpha particle. So when it hits it, it reflects off at a big angle. Now, at this stage, scientists perceive the atom as the nucleus comprises most of the mass of the atom, but it does occupy a really small volume of it. Typical atomic radius is 100 picometers, where the radius of the atomic nucleus is only about 5 times 10 to the minus 3, is super small. So you could think of like the atom as like the Superdome, if you've ever been there. Sit on the seats, you feel it's really big. Even when you're sitting, you feel like you're going to fall. Or any big football stadium, for example. And like the nucleus is like a marble on the 50-yard line in the middle there. Yeah, so big, a bunch of empty space, right, where electrons are flying around. And we have this really small sort of spot that has a lot of very heavy, dense particles that are positively charged, which is our nucleus. Now, the neutron was also discovered, and actually wasn't sort of discovered until the 30s and 1932 by a guy named James Chadwick. It was always thought that in addition to protons in the nucleus, there had to be maybe some other particle present. And Chadwick did a lot of experiments with alpha particles. And he noticed that when he did these experiments, energy was sort of given off that was very similar to gamma rays. And as we talked about, gamma rays are gamma particles, really the rays, have no charge. So later experiments show that they are neutral sort of particles, and they have a mass of 1.67495 times 10 to the minus 24. If you go out to this many decimal places and you compare it to the mass of the proton that we just saw, actually the neutron is the heaviest particle of all three particles, just barely. It just barely beats out the protons by at the third decimal place. So Chadwick named these guys neutrons. So what we have here, again, when we think about the nucleus, we have our protons, which are positively charged, our neutrons, which have no charge. And each of these guys individually are 1,800 or so times heavier than any electron that's flying around. So that also, again, backs up the idea that the nucleus itself is the most massive part of the atom, because in the nucleus we have protons, which protons are about 1,800 times heavier than an electron, and also neutrons, which are also 1,800 or so times heavier than an electron. And both of those particles are in the nucleus, and that makes it the most massive part or heaviest part of the atom, with our very small light electrons, again, moving around in that empty space. Any questions on that there? So here again is a comparison, and you can see here neutrons just barely at the third decimal place, beats out the protons. So heaviest, pretty close to heaviest, second, and the least massive of all those particles. So I think you should know which one is the heaviest, which one is the lightest of these three particles. I will say probably knowing the mass of an electron is probably a good number as you continue on in your chemistry career. I don't know if you'll necessarily need it for our class per se memorize, but as you go on, they may want you to kind of know those sort of numbers. All right, so let's then talk then about sort of the modern concept of atom. And this is again basically a nuclear view of the atom. All this sort of pinkish area here, this is the electron cloud, and really that empty space. That is where electrons are hanging out. As you see, super small, and here's our nucleus. And this is actually an electron density sort of map, if you will. You can maybe pick up on the screen, I think, that, as we're closer to the nucleus, it's a little darker sort of pink or reddish. And as you kind of move away from the nucleus, it gets a little bit lighter in terms of that pink color. And what that tells us is because of that attraction between the negatively charged electrons and the positively charged nucleus, it's pretty highly probable that you could find an electron near the nucleus. As we'll talk about in a later chapter, we don't really know how it got there, how it's actually moving, but there's a pretty good probability that an electron should be somewhere near that nucleus, as you can see by sort of the dark area here. But as you move out to the outside, the probability of finding an electron maybe decreases a little bit. It doesn't mean you cannot find an electron on the outside there, but the chances of finding an electron are a little bit less than what it would be if you're closer to the nucleus, because again, on the outside, it's not going to feel as much of a positive pull to the inside. All right, here. So the chemistry of atoms do come from its electrons. So as we've been talking about in a chemical reaction, the only thing that's happening is uh, bonds are being broken, which is all about electrons. The recombine and make different compounds by breaking bonds and making new bonds. In a normal chemical reaction, we never ever touch what's in the nucleus. So we never touch protons or neutrons. It's all about those electrons. And if you think about sort of the structure of the atom that we just saw, it does sort of make sense because electrons are on the outside flying around. So when two atoms come together, pretty much the first people can say hello to each other are electrons, right? They're on the outside. So that's where normal sort of chemical sort of reactions occur and bonds being made or broken occur. I think we're actually going to lay it up right now at that point. Any questions?